In this lecture 19, we saw the general form that a normal operator on a real inner product space of finite dimension can have. What we need from immediate recent lectures is the notion of complexification. That's when we have a real vector space, then we add to it an imaginary part, which is the complexification of that vector space. And then we can also complexify operators on real vector space by letting them add on complex vectors simply by acting on the real part and imaginary part independently. So as we move forward, we now have this property that we have seen already some time ago. That's a key and central property that we use, and it feels like we didn't use it very much, but as you see, we used it quite a lot. Is the property that complex operators have and real operators do not necessarily have. It is complex operators on finite dimensional vector space. They always have eigenvalues. Then, moving to properties learned not so recently, we have a definition of normal operator, and which is characterized by two main properties. First, that if we write its matrix with respect to an orthonormal basis and take the complex conjugate of that matrix, we get the same matrix again. This characterizes a normal operator, but another characterization of normal operator is that the norm of this operator applied to some vector always coincides with the norm of its adjoint applied to that vector. This was a very important property of normal operators that we used. Then the notion of invariant subspaces. So an invariant subspace is one where when we write the matrix of the operator with respect to some basis, and the basis contains a base for that subspace, then the parts, the columns of the matrix that correspond to this subspace, they will have non-zero elements only in the rows that also correspond to that subspace. That, of course, if we write all those vectors together, if we write those vectors far from each other, it gets a little more messy. Finally, for the orthogonal complement, it is we have a subspace of our inner product space, and we consider another subspace given by all those vectors which are orthogonal to this subspace, and then from there we can also define it through a basis. If we take an orthonormal basis, E1, EM, for this subspace, and we add more orthonormal vectors to that basis, so that together we get a basis for the whole space, then the vectors we add, they form an orthonormal basis for the orthogonal complement. And conversely, we can take any orthonormal basis for the complement, put it together, and write the complete list, which has an orthonormal basis for a vector space, together with an orthonormal basis for its orthogonal complement, and this list altogether will give us a basis for the entire space. And now, if we go to the topic of today's lecture, which is the description of real normal operators, what we have is an orthonormal basis such that the operator written as a matrix with respect to that basis will have little blocks, little 2 by 2 blocks, also 1 by 1 blocks, all in the diagonal, so this is called the block diagonal matrix, so that these 1 by 1 blocks, they are all real eigenvalues of the operator, and the 2 by 2 blocks, they are a way to represent the complex eigenvalues of course, the complexification of that operator, and the eigenvalues, they are of this form a plus or minus ib, where a and b are exactly the numbers that we see in these blocks. Here the numbers, this a and b don't need to be the same as this a and b. Also these a's, they can be different numbers. And in order to prove that, we have combined all these previous properties. So the property of being a normal operator in the sense that TV equals T star V in norm. Then the notion of invariant spaces and orthogonal complement to get this proof. And it was a key point in the proof that complex operators have eigenvalues. And of course, in order to use something which is true for complex operators and use it to talk about the real operators, we had to use complexification. And to see that a complex eigenvalue with the corresponding complex eigenvector of the complexification of an operator always gives us a 2 by 2 block which is invariant, so it has zeros. So meaning there are two vectors such that the span of those two vectors is invariant under T. That's when we get the zeros here. And to get the zeros here, we use the fact that the operator is normal, so it preserves norms, and the fact that we have 0 here implies that we have 0 here as well. And then the orthogonal complement is just so that we can apply induction and restrict now the operator to the remaining subspace and repeat the same argument again. If it has an eigenvalue, if it's complex, we get something like this. If it's real, we get something like this, and we can reduce the dimension again and again to get this description. So this is a summary of the lecture that we had today, and I will comment on some of the feedback of the students. Many students mentioned that this theorem is an extension of the real spectral theorem. I think it makes a lot of sense to phrase it this way. It was very nice to see it. It is a very beautiful way to phrase it. So a spectral theorem would be for only this part of the operator, and now we extend it. We allow operators which are not only self-adjoint, but also have this part here, which we are also including now. Many other students pointed out that the lecture used a lot complexification and existence of eigenvectors, and I would agree with that, especially because even though we only used it once, when we do an argument by induction, we are actually using it many, many times. Also, some students pointed out that now we can see the use of complexification. I would agree with that to the extent that it was really the use of a property of complex vector spaces that now allows us to deduce something about real vector spaces. But it's of course good to point out that we've been able to say something about the parity of eigenvalues, to define the characteristic polynomial of real operators, and to prove Cayley-Hamilton theorem from there, using also complexification already. Another comment made by students was that these little blocks 2 by 2 that we see here, they are real operators that act like complex operators, which I think is a very good intuition, a very good description for what these blocks mean. Now, some students mentioned that this form that we have here describes the operators with respect to this form that we have here describes the operator with respect to some basis. And I think it's interesting to notice that it is actually an orthonormal basis. Now, other students mentioned that this lecture incorporates some new concepts, and I would say that except for this idea that the 2 by 2 blocks, they are real operators acting like complex, there were no new concepts in this lecture. In this lecture we just had a theorem that says an operator is normal if and only if it looks like this. Then some other students pointed out that the block diagonal notion is very related to what we saw for nilpotent operators, and I would say they have very little in common, actually, in my opinion, except for the notion that block diagonal is a simple description for an operator. So whenever you can write the matrix of an operator such that it's block diagonal, this is, well, maybe not as good as being diagonal, which means just n numbers on the diagonal and 0 elsewhere. Of course, it's not as good as that, but it is much better than a matrix full of numbers all over. So that's so block diagonal in general is good because that's a simple way to describe an operator. And of course, we can give a description for nilpotent operators, which is block diagonal. That's good. We can also give a description for normal operators as block diagonal, which is also great. But the two are not so related, except for the fact that, as I said, block diagonal is a good way to say that the matrix is in a very simple and convenient form for us to work with. Now, some students felt that the topics we saw today, the construction and the theorem, they were not so much related to complexification. And I believe this misses the main point, which, as I said, is that we did a proof by induction. So, yeah, we only used properties of normal operators and complexification to get in an invariant subspace. We only used it once, but we used it once exactly because we did a proof by induction. So actually we used it as many times as the dimension of the space itself. So let's say we use it quite a lot, actually. Also, some students pointed out that this topic was very much related to Jordan bases, and I would say it is not so related to Jordan bases. Actually, this is the complementary case. Jordan bases is sometimes the best description we can give to complex operators when they are not diagonalizable. And here we're talking about complex operators which are diagonalizable, and a block diagonal matrix is not upper triangular because it has these elements here which are below the diagonal. So that's very different from a Jordan basis which only had these elements as non-zero without these ones. This is a good summary for today's lecture. I hope it's useful.